Hello, this is Mr. Gilmore with the 9.1 Circles, Chords, Arcs, and Central Angles lesson. Today we begin our journey into circles, where we are going to start with several definitions as we dissect the circle into its components, and then we'll actually look at a good number of theorems. However, these theorems we're going to dive into do require a certain assumption that we make about the measure of an arc, and we'll take a look at that when we approach our definition of central angle. Let's start with what a circle is. A circle is the set of points in a plane, a given distance from a given point. Now, the given point we call the center of our circle, and we name our circles using that given point. So the given point, right, obviously we use capital letters to name points. That becomes the name of our circle. Down below, we have a diagram of circle A. Circle A, because the center point, the given point, we've labeled with the capital letter A, then becomes the name of our circle. Point B is a point on the circle. In other words, point B belongs to the set of points that are a given distance from that given point A. So point B, we find, will be part of our circle. It's on the circle. We use that preposition there. And we'll find relationships between the points on the circle and the center of the circle. So there's this given distance from the center of the circle to a point on the circle. If we were to connect those two, if we were to connect a point at the center of the circle to a point on the circle, we call that the radius of a circle. So a radius is a segment that begins at the center and ends on the circle. By definition, since this is a fixed distance, every radius of a circle equals every other, because if we choose any point on the circle, it's a given fixed distance from the center, meaning all radii, plural of radius, all radii will be the same length. Okay, and we actually use the definition of radius then as our justification to say that we know all radii are equal in measure. A chord is another type of segment we find inside of a circle. A chord is a segment whose endpoints lie on the circle. In other words, choose 2 points on a circle, connect it with a segment, you've got yourself a chord. However, there are special kinds of chords. We call them diameters. A diameter is a special chord in which passes through the center of our circle. In other words, the endpoints and the center will be collinear. That's when we have ourselves a diameter. Down below in our diagram, we have the radius AG, AJ, and AK. By definition, we see that it's a segment from the center of the circle produced to be or to the endpoint on the circle. We also have chords of HI and JK. HI, its endpoints are on the circle. So same goes for JK. However, JK is a special kind of chord. Since it does pass through our center, we call that our diameter JK. We are going to be allowed to assume that any point that appears to be the center of the circle is, and we're also allowed to assume that any segment that appears to pass through the center of the circle is a diameter. So yes, you're allowed to assume that if it appears to be a diameter, then it is a diameter. We'll see there in some cases, though, we will that we're not allowed that assumption. However, we make that statement when we begin our proof of things. The circumference of a circle is another important part of the circle. We'll talk a lot about the circumference and relationship as we see when we introduce this idea of what's called a central angle. But a circumference of a circle, so imagine picking any point that's on the circle. Now, from that point, begin following the other points that are on the circle around the circle until you arrive back to that point you've chosen. What you've then traversed is really then the distance around the circle called the circumference. So if we take a look at our diagram below, if we were to pick point A and then travel around as all the points on the circle all the way around back to point A, well, again, we have then traveled the circumference of the circle. It's very much like if we were to travel around any given polygon, we give that the perimeter name. We call this around the circle the circumference name. Now, we can then take our circumference and chop it up into smaller pieces of our circle, essentially portions of the circle that connect points on the circle. We call these arcs. So an arc, again, is a portion of a circle that connects points on that circle. Now, we want to actually take arcs because if I were to pick any 2 points on any given circle, there's a direction that also needs to be chosen. I can choose the shortest path between those 2 points, or essentially I can go a clockwise direction or a counterclockwise direction. So if I were to then choose 2 points on a circle, and I want then, if I find the path then to be less than half the circle, we want to give this portion of an arc a specific name, where of like a specific category of arc, we call those minor arcs. So a minor arcs are less than half a circle. Of course, if I picked any 2 points in a circle and I traveled longer distance around from one point to the other, I would find what's called a major arc. So major arcs are more than half a circle, and a semicircle are arcs. Yes, semicircles are arcs that are precisely half a circle. If we take a look at our third diagram down there, we see our semicircle, and it is we do find, in fact, that segment from one point on the circle to the other point on the circle is in fact a diameter. It's one of the theorems we actually prove in one of our homework assignments, is that the diameters do cut semicircles, or there's also the converse, which is true, which is semicircles are cut by diameters. Now, since we have these new these are not new segments for us, but these are new objects that we need to name with the circle. We need to know how to name our arcs. Now, we use actually a naming system that allows the user to understand whether or not we're referring to it as a minor arc or a major arc. So for a minor arc, we just use 2 letters. So pick the 2 letters, 2 points that are on a circle, then connect those 2 points. You're looking at that then being a minor arc of the circle because it specifically uses 2 letters. So if we want the user then to know, the reader to know that we're going then with a major arc, we're going to use 3 letters. So down below then in our example, if I were to pick 3 letters, that means I'm referring to either a semicircle or a major arc. We have the example of ADB. So notice that our minor arc goes from just simply A to B, which would be the shortest path we could take. That's just the minor arc less than half a circle. But if I was going to do the major arc, I'd go ADB, which is then the longer path all the way around the circle from point A to point back to point B. And we find that to be greater than half a circle, which means that we're dealing with a major arc. Semicircles are also use 3 letters to name them. So in our diagram, we actually have 2 semicircles, ADC and ABC. So notice that with a semicircle, I can't just say, hey, look at semicircle AC. Wouldn't know which direction I'm going from point A to point C. So ABC and ADC, choosing that middle letter gives the reader a direction of naming that arc or finding that appropriate object within the given diagram. All right, now we move on to central angles. Okay, so since we can form this construction of radii inside of a circle, right? This radius of a segment from the center of the circle to a point on the circle. Well, what happens if we then have 2 radii drawn into our circle? Well, what it forms is then an angle within our circle, and we call that angle a central angle. In other words, an angle in which its vertex lies at the center of the circle. So in our diagram here, we have central angle ACB. But you'll notice that this central angle is actually related to the circle in a way. You'll notice that from point A to point B, there's this arc that is formed from the creation of this central angle. Now, this central angle, then, we're going to use this phrase cuts. That central angle is cutting that arc in our circle, arc AB. What we're going to find is there's going to be an assumption we make about the relationship of the measure of our central angle to the measure of that arc. So we have then our first postulate, the arc measure postulate, or AMP, A-M-P. The measure of an arc, or the arc measure, equals the measure of the central angle that cuts it. In other words, that this angle here in our circle, this central angle, it has some measure to it, right? Some measure in degrees. What we're then saying is that the rotation of this arc here from point A to point B will also have that same measure, okay? So the measure of arc AB equals the measure of central angle ACB. So we could play a simple game. If I were to give you the measure of the central angle, let's say the central angle measures 100 degrees, then the measure of the arc also is 100 degrees. If I were to say then the measure of our central angle was 25 degrees, then the measure of our arc is 25 degrees. And the definition works forward and backward, which means if I give you the measure of the arc, you'll also know the measure of the central angle. So if the measure of the arc, let's say, is 70 degrees, then the measure of our central angle is also 70 degrees. I should say the central angle that cuts that arc also measures 70 degrees. Now, so there's 2 little theorems that we can prove very quickly with this new definition, or the definition of central angle and this new arc measure postulate that we have relating the measure of our central angle to the measure of the arc. These 2 little theorems I'm going to have you guys do on your own on the worksheet. They're very simple. So given any circle, that if you were to have then 2 central angles of equal measure, then they cut arcs of equal measure. So down in the diagram, if you're given then that NCO is equal to our central angle of PCQ, then you can prove then that the measure of arc NO will equal the measure of arc PQ. That's one of the first proofs you'll do. However, the converse is also true, which means, let's say the measure of this arc here, NCO, and the measure of our arc PQ are given to us as being the same. That means we can prove then the central angles that cut them will also be the same measure. And so we'll find that there's two theorems here, and they're very short theorems. Thanks to this postulate we have, the arc measure postulate, we can actually prove that equal central angles cut equal arcs, and that equal arcs are cut by equal central angles. However, we will move on to some theorems in which I'm going to walk you through because there's a little bit of some subtlety here as we introduce this arc measure postulate, and also the relationship that we find with trying to prove some other relations we find with these segments that we can form with inside of our circles. And that's what we're going to finish off the day with, is just looking at several theorems in which we can prove using our circles, or using found within circles. So the first one we'll look at here is what we call chords of equal measure. There are some theorems we just don't have names for. We'll just go by the theorem number we find on the postulate theorem handout. So in this case, this number is probably like 9 point something, 9.3 or 9.4, somewhere around there, where we'll prove that the chords of equal measure are actually cutting arcs of equal measure. So in a circle, chords of equal length cut arcs of equal measure. In other words, look at our diagram below. We are given that BC is equal to DE. We're going to prove that BC, the measure of arc BC, is equal to the measure of arc DE. So notice we use that little M to represent the measure of the arc. And notice with the name of the arc, we place these little arc marks over top of it. So we're given that BC and DE are equal. We're going to prove then is that the arc BC and the arc DE are also equal in measure. All right, now on the next slide here, let's jump into the proof. So the proof of this is very simple. What we're first given is that BC is equal to DE. Well, we've got a very simple construction to make. We're simply just going to take point A and connect to point B, connect A to point C, connect A to point E, and connect A to point D. By doing that, we form radii of our circle AB, AC, AE, and AD. And what we then know by definition of that radius is this. We know that all four of those newly formed segments are equal in measure. Well, what does that tell us? That tells us that we actually then have two congruent triangles. So very interesting that we're using pointies, right? These polygons that we studied back in first semester, pointies, to prove something about roundies. Isn't that interesting? So what we find here is that our two triangles ABC and ADE are actually congruent to each other by side, side, side. So then by our good pal CPCTE, we know that their central angle measures here are equal. Well, what we just proved was that central angles of equal measure will cut arcs of equal measure as well. So moreover, we know then that the arcs that they're cutting, which are specifically arc BC and arc DE, those two arcs are now equal in measure because equal central angles cut equal arcs. And there we have it, the proof that equal chords, chords of equal length, will cut arcs of equal measure. Let's take a look at another relationship that we find within inside of a circle. Now, this one actually comes in handy quite often, not just in our chapter, but also on the myriad. We'll actually use this theorem here whenever you have a diameter perpendicular to a chord, or really, I should say, any segment, or it could be a radius perpendicular to a chord even, we're going to find that it will actually bisect that chord, and it also cuts the arc in half as well. So diameters perpendicular to chords. Let's take a look at this theorem. If a diameter or radius is perpendicular to a chord, then it bisects that chord and the arc that it cuts. And so we're given here that BC, our diameter, is actually perpendicular to our chord EF. We're actually going to prove two things. The first thing is we're going to prove that ED is going to be equal to DF. We're going to prove that D is the midpoint of that given chord, but also that it does cut these arcs here into equal measure as well, that EB will equal the measure of BF as well. Let's take a look at that proof. So here's the proof of our perpendicular diameters. So again, we're given BC is perpendicular to EF, and we're going to prove that it does two things. It's going to cut the chord in half, ED equals DF, and it's going to cut the arc EF in half, so the measure of arc EB will equal the measure of arc BF. So we're given diameter BC and non-diameter chord EF, and again that BC is perpendicular to EF. Let's do some constructions. Let's connect point A to point E and point A to point F. By doing that, we form a pair of radii, and we know that with any given circle, by the definition of radius, we have equal segments here. So we know, we know that those two segments, AE and AF, are equal to each other. Now, something else we know. Since since BC is perpendicular to EF, we know we actually have right angles. Okay, we have right angles there because of the perpendicular lines theorem. And these two triangles have a common side. They both share side AD. What we're leading up to, again, is some congruence. We actually do have congruence between these two triangles now. ADE and ADF are congruent by HL, our special case hypotenuse leg. Remember, with that one, we need equal hypotenuses, which happen to be our radii. We need equal pair of legs, which happen to be that common side. And the triangles need to be right triangles, which we do have that because we're given they're perpendicular. So thus, by CPCTE, right off the bat, then we can claim ED is equal to DF. But there's a second thing we want to claim from that congruence, and that is we know angle EAD and angle FAD, those two angles there, are equal in measure. Well, because those are central angles, and equal central angles will cut arcs of equal length. So because of that, now we know the measure of arc EB is equal to the measure of arc BF, because equal central angles, again, cut equal arcs. So using that, one of those two tiny little theorems we just saw before jumping into these major proofs here. Let's take a look at another one. This was actually a little bit of a tricky proof, and so I'm going to walk you through this one. So this is known as the perpendicular bisector of a chord. So let's say you're given any chord inside the circle. In our case, we're going to have this chord EF. Let's say we then form a second segment that is a perpendicular bisector of that given chord, which means this segment here, BC, is not just perpendicular to this segment, but it's passing through the midpoint of that segment as well. So D is a midpoint, and BC is perpendicular to EF. What we're going to prove is that the perpendicular bisector of a chord passes through the center of the circle. In other words, let's prove that BC here is a diameter. So it appears that BC is a diameter, however, we really don't know. You'll notice that I took away the center point A. So since center point A is not there, we can't assume that BC is a diameter just by looking at it. What we're going to do is prove that BC is a diameter. So our approach to this one, how are we going to prove that BC is a diameter if we do know then that BC is perpendicular to our segment EF and that it's a bisector of our segment EF? This is where things get a little fun with this proof. We're going to do this one indirectly. Yeah, that's right. Indirect proof for this one. It's a neat proof. So let's take a look then. We're given again that BC is perpendicular to EF. We are also given that ED and DF are equal to each other. We're going to prove that BC is a diameter. So what's our assumption going to be if we're going to do this indirect? Our assumption then is that BC does not pass through the center of our circle. So if BC is not the diameter, that means the center point A, which is called center point A, is not on BC. So center point A, I'm going to put right here. Okay, center point A. So there's our center A. Okay, so if BC is not a diameter, but there's our center point A, that means there is a diameter that does pass through point A and point D, because point D, right, is not on a diameter, not part of the diameter BC. That means there is a diameter that does pass through point D and point A. So there's our diameter. Okay. So this newly formed segment here is a diameter that does pass through our center point A. But then something kind of wonky goes on by us assuming that, again, BC is not a diameter. So if BC is not a diameter, then there is a center point called A, and there must be a diameter that does pass through it. Let's call through it, that the center and point D. So if AD is a diameter that passes through the midpoint of a chord EF, so here's where it gets really fun. Since AD, this diameter, does pass through the midpoint of a segment, we just proved there's actually a converse to our proof we saw earlier, which is if a diameter passes through the center of a chord, then it must be, if it bisects a chord, it must be perpendicular to that chord. Well, that means since this diameter AD is passing through the center of our chord EF, it's also perpendicular, which means this angle ADF is a right angle. Well, things then begin to fall apart here, because if angle ADF is a right angle, this is impossible because angle CDF is also given to as a right angle, but CDF is part of the whole thing, ADF, and the part cannot equal the whole. We're saying that CDF and ADF are equal in measure, and that's impossible for us here, which then means we arrive to a contradiction, all right, because again, the whole cannot be equal to the part cannot be greater than the whole, the part cannot be equal to the whole is always going to be greater than the part, which then means the assumption that we made that BC is not a diameter, that's false. So BC must be a diameter, thus it does pass through the center of our circle. The question that may come up would then be, well, what if point A was on the other side? What if point A was here? Same story would happen if we were then to do this diameter AD. We'd still run into that, be a right angle, and again, that would mean that the part and the whole are equal in measure. That's impossible, which then means we run into the exact same conclusion that our assumption is false, thus making BC a diameter so if we do run into any given chord such that there is a second segment that's a perpendicular bisector of that given chord, you do know guaranteed that it is a diameter. Let's take a look at one more theorem together. One more theorem. This one is talking about, again, some chords of equal length. However, we're looking at it from a different approach, not looking at the arcs that they cut, but rather the distance they are from the center of a circle. Now, when we're talking about distance, that means it's the perpendicular segments, the shortest length from the point to that given segment. So in a circle, chords of equal length are equidistant from the center. In other words, if we take a look at our diagram, what we're given to us is that BC and DE are equal in measure. What we're going to prove then is that AF is equal to AG, meaning that the chords are going to be equidistant. Now, in the diagram, I've already got them labeled as perpendicular. Why? Because distance means that shortest path, and we found that our shortest path is the perpendicular from that point to the given segment. So AF and AG are perpendicular to our segments BC and DE. Let's take a look at the proof of this one together. So the proof of this one actually is not too tricky because we're going to use some of the previously proven theorems that we saw here earlier about diameters or radii that are perpendicular to a chord, what we can learn from that. So we're given, again, BC and DE are equal. Okay, we're going to prove that AF and AG are equal. How we're going to do this? We're going to go through congruence one more time. So given BC and DE are equal, then let's connect point A to point B and point A to point E. Now you notice that we formed two triangles, AFB and AGE. We're going to prove that those two triangles are in fact congruent to each other. So first off, by definition, we know that since AB and AE are radii, we can call those two segments equal to each other by definition. But the thing is, we're given, since that AF and AG are the distance from the center to the chord, those are the perpendiculars, which means we have a radius or part of a radius or part of a diameter that's perpendicular to a chord, which means because AF and AG are perpendicular bisectors, that means they are perpendicular bisectors of the chords, which then means that BF and GE are equal. In other words, actually all four of those halves are equal because equal halves or equal wholes have equal halves, and that means we have those segments BF and GE equal to each other because, again, halves of equals are equal. And that means, since they're perpendicular bisectors of those chords, we then know that they're right triangles by the perpendicular lines theorem. We know that AFB and AGE are right angles, which then means we have hypotenuse leg to prove that these two triangles are actually congruent to each other. So triangle ABF is congruent to triangle AEG by hypotenuse leg, which is all we need, because then we notice their corresponding sides, AF and AG, are equal to one another by CPCTE, and there we have it, that chords of equal length are actually equidistant from the center of our circle. All right, so we've come to the end of our lesson 9.1. We dissected a circle with many different definitions. We took a look at what a circle is by definition, the segments that are formed inside a circle, the circumference of a circle. We also dove into this major assumption we make about the circle and its central angles, that they cut arcs of the same measure. And using the arcs of the same measure, we actually can approach then our other relationships we find with chords, essentially arcs and chords related with inside the circle, and also some other information about chords when we run into chords of equal length or diameters passing through chords, we have those relationships as well. So be sure to hop over and take a look at the 9.1 worksheet, where you'll dive right into some of the relationships of circles, proving several different things about the circle as we look at the relationships formed, again, between the segments we can find and the central angles that we form. If you do have any questions on that worksheet, please do not hesitate to email me with that. Be good and do good.